Electrodynamics. One of the things we need to consider is what happens when you put charges near matter. That matter could be an electric conductor, and then we know that the charges can move, but it could also be an insulator where the charges really can't move, but it still does something. So let's look at polarization, which is the process of a material getting influenced by some charge. And I'm going to start with the simplest problem that we can deal with, and then we'll make a more complicated problem. So imagine that I have a hydrogen atom, like that. So a hydrogen atom we can imagine as a nucleus, which is just a proton, and an electron, which we're going to represent as an electron cloud, right? We don't say the electron's here, the electron's there. We just kind of give it a probability density, and that gives it this, makes it act electrically like it's smeared out over all that region. Now suppose I put a charge Q right here. So this has a charge of, well, I guess that would be E, and this would be negative E. Okay, we'll use that. That's fine. So what's going to happen? Well, we know that this charge is going to make an electric field over here, and that electric field is going to push that positive charge. So what's going to happen is that that positive nucleus is going to get pushed that way, or really the electron cloud will be pulled the other way. So it's as though we have a charge separation right there. That charge right here causes this to polarize. Now remember that we can define an electric dipole moment P as the sum over I, QI, RI. So in this case, if I just take this as my origin, the center right there, then the polarization P, and let's call this the x-axis, and let's call this the distance r away. Then the polarization P is just going to be equal to the separation distance vector, which is in the x direction, times the charge. I'll call that E, D, and then we'll say the vector, actually this is going to be the vector from negative 1, 0, 0. It's from the negative charge to the positive charge. Okay, so that's our electric dipole moment. Now once we describe a charge distribution with a dipole moment, then we can calculate the electric field due to that. So this charge is going to polarize this atom. This atom isn't going to make a dipole moment. That atom isn't going to make an electric field over here, and there will be an interaction. So this is why we have an electric interaction between charged objects and neutral objects. Let's do this problem. Let's find the force on that charge due to this. Now, one of the things that we're going to have is what we call polarizability. So we're going to say the dipole moment P is going to be some constant alpha times the electric field applied. So alpha is the polarizability. It tells us how much these things separate when a charge comes in near it. And so that depends on the atom or the molecule. Molecules can be polarized too. So if that's the case, I want to use that to find the force on this. So let's start off with number 1. I have a lot of space here. I'm going to write it over here. 1, calculate E at atom. I'm going to take that charge and calculate the electric field over here. 2, calculate P. Right, so now once I know the electric field over there, I can calculate the dipole moment. 3, calculate E due to dipole, I'll call it ED, at Q. So once I have an electric dipole moment over here, I can use that to calculate the electric field over there. And then 4, easy, calc the force. Once I know the electric field, I just take the electric field due to this and multiply by that charge. It's kind of a weird thing, right? Because, you know, we have this charge that makes an electric field that interacts with the charge, right? Okay, step 1. E, I'm going to call it EQ. EQ, I'm going to write it as a vector. It's going to be equal to negative 1 over 4 pi epsilon naught Q over r squared times the vector 1, 0, 0. Everything's in the x direction, so it's not that big of a deal, but I just did it anyway. All right, so this is just a point charge. I can calculate the electric field to that point charge. It's going to be this way in the negative direction, and there we go. Now 2, I can calculate the electric dipole moment P. P is going to be equal to alpha times E. So that's also going to be in the negative x direction. So all I have to do is multiply this by, I'm gonna switch. I'm not going to write the vectors. Everything's in the x direction. I'm going to put this negative and positive there. So this is going to be negative 1 over 4 pi epsilon naught q alpha over r squared in the negative x direction. All right, so I just took that electric field, applied there, found the dipole moment. Now we have to remember, how do we calculate the electric field due to a dipole? Well, there's two formulas for that. The one I like, E due to the dipole, is going to be equal to 3 P dot r hat times r hat minus P over 4 pi epsilon naught r cubed. That's the one I like because it uses these, we can do this in Cartesian coordinates. There is the polar coordinate version of that too that says ER is going to be equal to 2p cosine, I can't remember, cosine theta over 4 pi epsilon naught r cubed. And then E theta is going to be p sine theta over 4 pi epsilon naught r cubed. So over here, if I use the polar coordinate version and the spherical coordinate version, my r vector is this way, right? And my p vector is this way. So I'm going to get a theta of 180 degrees, so that's negative 1. I'm going to get a theta component of the electric field is 0, because sine is 180, sine of 180 is 0. I kind of like this one better, but it doesn't really matter. Let's just use that one because we don't have to do any algebra. So I can now calculate E due to the dipole. It's going to be equal to 2 times P, but this is P. I've already taken into account the sign, right? Yeah. So I'm going to get a negative in there, and that's already there. So it's this, that already took this into account, the direction, right? That's why I got the 180 degrees. So 2 times P, which is 1 over 4 pi epsilon naught q alpha over r squared, 2p. Cosine theta is negative 1. I already put that there. And then I have r cubed, 1 over r cubed. And then I have 1 over 4 pi epsilon naught. So I have two of these. And then I have an r squared and an r to the 5th. Now I can calculate the electric force, which I ran out of room over there. So I'm going to delete this stuff and put it right here. F is going to be Q times E dipole. So notice that this is in the negative direction, and that's a positive charge, so I am going to get a force this way. It's going to be an attractive force. So now all I have to do is multiply that by Q. Let's just combine things together. I get F negative 1 over 4 pi epsilon naught squared, because I have two of those. Then I have the 2. Then I have a Q times Q, so I have a Q squared. I have the alpha. And that's where those charges are in the E alpha, right? So I don't have to write that in terms of what charges they are. If I know the alpha, I know the polar. I'm just going to write it in terms of the dipole moment. And then I get over r to the 5th. And that's in the negative x direction. And there you go. So this 1 over r to the 5th, remember, it's not going to get up to an infinite thing, because an infinite force, or super high, because this approximation is only when we're far away from the dipole moment. Okay. But as you get further away, it gets super weak. That's for sure. As r increases, that goes super weak. Okay, so that's the simplest polarization problem you can see. But the thing here that we're looking at is this charge makes an electric field, but that's not the only situation. Whatever electric field that makes is complicated by the response to the material. The material is going to have a response, and that's that polarization. Okay, now let's do something fun in Python. What if I replace my atom with a plastic block? So here's my block. And then I have a charge right there. So that charge is going to make an electric field in this plastic block. And the plastic block will be polarized. And so we'll get these polarization vectors, something like this. And then all those vectors will create an electric field over there, and then we can find the electric force on that thing. Of course, you know that I'm going to do this numerically because I want to make a nice visual. So instead of having a block with 10 to the 24th particles in there, and each one of those particles can be polarized, I'm going to make 125 particles or something like that. 5 by 5 by 5, something like that. And then I'm going to take that block, I'm going to calculate the electric field at all those locations, and then I'll say, again, P is going to be equal to alpha E. So once I find the electric field at those locations, I can then calculate the dipole moment P. I switch those things a lot. We have the dipole moment P, and then later we're going to look at the dipole moment per unit volume, which is called the polarization. Sorry about that. But we're just calculating the dipole moment for all these things. They all make an electric field over here, and then I can use that to calculate the force right there. Let's get to it. We got a lot of work to do, so we better get started right now. Okay, so here I am in Python. Now, I've already put a couple things in there just so I can save it. What I need to do is to make my grid. And so I have an L size box. I want to go ahead and make my box with my points. I'm going to do this a couple different ways. Let's just make the points, and then we can add it as a list later. So if I want it to be L by L, I need, let's say I want, I'm picking 6. I don't know why, I'm going to do 6 points. The first thing I want to know is how big of a step size am I going to make. So let's say my step size is going to be equal to L over N. Did I do L over N plus 1? No, let's just do L over N. So that's how much I'm going to move in each direction. Now I need my starting location. So let's call this RS. It's my starting location. I'm going to start at the lower left-hand corner. Vector negative L over 2, negative L over 2, negative L over 2. And we're going to fix that in a little bit. Don't worry about that. And what I'm going to do is move in the X direction, move in the Y direction, move in the Z direction. So I'm going to have 3 loops. While RS dot Z is less than L over 2, while RS dot Y is less than L over 2, while RS dot X is less than L over 2. Now, once I'm going to go through my X loop and move my point. So I'm just going to say RS equals RS plus the vector I'm moving in the X direction, ds 0, 0. And let's put a sphere there. Sphere position equals RS. And let's give it a size of radius equal, we're going to get rid of this in a little bit. Let's say L over 20. Now, that's going to move me through my loop in the X direction. And when I get done with that, I'm going to go back up here and do it again, but I need to reset my X value to negative L over 2. So RS dot X equals negative L over 2. If I don't do that, it's just going to go through the whole thing once. And the same thing up here, once I do my while loop, I'm going to have to reset my Y value. RS dot Y is equal to negative L over 2. So now once I finish with that X loop, I need to increase my Y value. So now I'm going to say RS is equal to RS plus vector 0 ds in the Y direction 0. And then when I'm done with that, I need to do it in the Z direction. RS equals RS plus vector 0, 0 ds. I think that should work. I just typed it really fast, so I couldn't have made a mistake. But you know, the best way to find out if you made a mistake is just to run it. And it worked. Look at that. I do want to do one thing just because it's fun. Let's make these a little bit smaller, 40. And then I'm going to put a rate statement here. So this is going to do 5. So let's do a rate of 5. So do 1 second per thing. No, that's going to be 25 seconds. Let's do 10. Okay. So now we're going to see them being built. And it's like watching, it's cool. And you can rotate that around. So it's building up in the, I started in the negative Z direction, and then I'm adding in the Y directions, and then I'm adding in the Z directions until I build up my little cube of points. Now, warning, we don't need to visualize this. You could do this without drawing the sphere, and that would make things run a lot faster. But this just looks cool. So I'm going to do it this way. But don't do n equals 50 or something like that, because that's going to be 50 by 50 by 50, and you're gonna regret it. I think you might regret it. Okay, let's do this. Let's put a box around that just so we can see. I'm going to call it a cube box. The position is going to be equal to vector 0, 0, 0. The size is equal to vector L, L. Oops, I missed that. L, L. And then I'm going to make it, oh, you can't see that, I'm sorry. And then I'm going to make it transparent, so opacity equals 0.3. Oops, 0.3. Let's run that. And I want to show you something that's, I'm going to get rid of this rate statement because that's just, no one's got time for that. But it is cool. So here you can see, oops, that my points and my cube don't match, right? They actually do match. It's just that I'm always using the left side of each point, and so that's why it looks off. And so I want to fix that just because I want to. So to do that, since I want to get to the center of the thing, right? So I'm going to start here with plus ds over 2, plus ds over 2, plus ds over 2. So I'm going to shift it that little bit amount. So I'm not going to start at the edge of each little step size. And then over here, I need to say these as plus ds over 2. And this one's going to be plus ds over 2. And that's that. Okay, now let's run it again and see what happens. It doesn't really matter because the physics is the same. Well, it didn't work. What did I do wrong? ds over 2, ds over 2, ds over 2, ds over 2. Negative x ds over 2. What did I do wrong? Well, I'm not seeing it. Well, I got that to work earlier. Not a big deal. Gonna proceed anyway. Okay, so I don't really care about drawing spheres there anyway, so it doesn't really matter what that looks like. What instead I want to do is to create a dipole moment at each location. And so I'm going to create these dipole moments as vectors. And I'm deciding here, let's just call it PS. It's my P's, right? The P's. And so it's an empty list. So down here, I'm going to add to my P's, I'm going to add an arrow. The position is going to be equal to this vector RS. The axis is going to be equal to, this is started off as 0, right? Because we're going to change this. Axis is going to be equal to vector 0, 0, 0. And then let's give it a color equals color.yellow. So it won't show anything because the axis is 0, but I have them all there. So if I run this, nothing really happens. It's just a box. Okay. Now, in order to calculate the dipole moment, I need to calculate the electric field. So I need to have a charge there. So let's go ahead and put a charge up here. I already have Q0 is 0. Let's just call it Q1. It's a sphere. Position is going to be equal to, I'm going to put it on the x-axis at L0, 0. Radius is going to be equal to, let's say, L over 30. And then color is red because it's positive. And let's say Q equals Q0. So I'm going to give it a charge property in there just so we can do that. If I run it, then there's my charge. Okay. Now what I want to do is to use that charge, and I need to calculate the electric field at all my different locations. So down here, I'm going to make a function called E, def E. And I'm going to give it an observation location, ROT, and I want to return the electric field at that location. So I'm going to say, I'm going to use that charge Q1. So the first thing I'm going to do is calculate the vector from Q1 to my observation location. So it's ROT minus q1.pos. Right? Q1's an object, so I need to use the vector location. And now I can go ahead and calculate the electric field at that location. It's just going to be k times q1.q times norm RT divided by mag RT squared. So that's the electric field due to a point charge. And then I'm going to return that. Okay. Now the next thing I need is my polarizability alpha. So let's say alpha is 0.1. And we may have to put a scale in there. I'm not sure. I don't want to put a scale in there. So let's just leave it as alpha is 0.1. If we make our alpha too big, that's fine. We could fix this thing later. I'm really making a visual. What I can do now is to go through my p's. So I can say for p in p's and calculate the electric field at that location and calculate the dipole moment. So the first, let's see what I'm going to do. I think I can do it right now. Just p dot axis equals alpha times E of P dot POS. So P dot POS is the vector location, so I'm going to pass that as my observation location, calculate electric field due to that point charge, and that will set the axis for that. I think this should do it. Let's see if I run this, if that works. Okay, see, now the fields are off a little bit. I could move my square and things like that, but I don't want to do that. And you'll notice the problem here is that the charge is very close, have very high dipole moments. The arrows are really big, and those are further away, so they're not as big. Let's change this to 5. I wonder if that does it. I think that does it. No? I'm not sure about that. I apologize for that. I don't want to waste my time figuring that thing out, but you could also shift the square over. Kind of perplexed. Why is that? 1, 2, 3, 4, well, whatever. So now I have my dipole moments. So what I can do now is to go backwards and make another function that calculates the electric field due to each dipole moment. So let's do that. So I'm going to go down here, and I'm going to say def ed ROT. So I'm going to give it an observation location, which is going to be my charge. I'm going to calculate the electric field due to that dipole moment. Due to the dipole moment, these dipole moments. Yeah, all of them. So I'm going to use the p's. So ET equals vector 0, 0, 0. So what I'm going to do is to calculate the electric field due to each moment and then add them all up, right? So I need to start with the 0 to add 2. For P in P's, I need to calculate that observation location. So RT is going to be ROT minus P dot POS. Now I need to calculate, update my ET. I'm going to do it in one fell swoop. ET plus K times 3 times, remember I'm using this formula up here, I had to erase it. It's dot P dot axis. P is my dipole moment. It's an arrow, but the axis of it, that is the vector value that I want. So I want P dot R hat. So R hat is going to be norm RT. And then I'm going to, after I take that dot product, I'm multiply it by norm RT. And then I'm going to subtract P dot axis. And this is where if you add a scale in there for your arrows, then you're going to have to undo the scale when you use the dot product and the other thing right there. And then divide by the 1 over 4 pi epsilon naught's in the K. So I just need to divide by R cubed. So that's going to be mag R, you can't see that, mag RT cubed. Okay, and that's going to go through all my things, and once I'm done, I can return ET. So what I'm going to do, I'm not going to calculate the force, I'm just going to draw an arrow to represent the force. I'm going to give it an E scale of 1. I don't know how big the arrow is going to be, so I'm just guessing. And now I'm just going to draw an arrow at that location. So arrow POS equals Q1.POS, axis equals E scale times ED of Q1.POS. All right, so I'm passing it the location of my charge to calculate the electric field. And then let's put the color at color dot cyan. And let's just see what kind of damage we do. I haven't saved this in a while. Save. Run it. Oh, see, huge. Okay, so let's go down here and let's say 0.001. I should print that out and I know how big it is, but okay, there. I guessed right. So there's the force on my charge, the electric field, and I multiply by positive charge, and you can see that it's in the right direction. So there you go. Polarizing that material, and that material makes an electric field that then adds to the total electric field and can cause a force and things like that. So there you go. Polarization, dipole moment, bunch of cool stuff. We're going to do some more things in the next video. Code down below. Talk to you later. That's it. Bye.